So welcome to DSD subject, that is module 2. In module 2, today we will see about adders and subtractors. In the previous class we have seen and means in this module 2 we have seen decoders, encoders, and after that we have seen the digital multiplexers. Okay, so how to realize the Boolean functions using the digital multiplexers. After seeing the multiplexers, so now today we will see what are adders and subtractors. Okay, so now, so basically, so adders and subtractors means, so those will do the basic, the operation, so what we call as the addition and subtraction. Okay, so addition and subtraction, the two operations. So what we will do with the, as of all of you know, we do with the adders and subtractors. Okay, so now these adders and subtractors in digital circuits, how we can realize. Okay, so before that, in digital means everything we will all the operations we will do with the binary numbers. Okay, so for that, so we need to know, so what is the binary addition and binary subtraction. Okay, so by knowing the binary addition and subtractions, so you will see the digital circuits which will do the binary addition and subtractions. Okay, so now, so basic, the adder, so adder will add the number of bits here. So as we are seeing on the screen, so it is half adder. Okay, so half adder in the sense, so here, so designate means in short form we can call as HA, half adder. So here in this half adder we will consider only 2 bits. 2 bits in the sense, suppose if it is A and B, 2 variables are there, A and B are 2 variables, we will take A as single bit and B as single bit. It can be 0 or 1, and B also it can be 0 or 1, means the single bit addition. So single bit addition we call as a half adder. Okay, so now if it is a single bit, if there are 2 variables like A and B, okay, the 2 single bit variables, A is 1 variable, B is 1 variable, both are single bit, means there are 4 possible combinations. It can be 0 0, it can be 0 1, it can be 1 0, and it can be 1 1. Okay, so there are 4 combinations are there. Okay, so 0 0 means 0 0, 0 1, 1 0, and 1 1. Okay, so now for this one, how, what is the addition in the binary? Okay, so if you see here, okay, so if you see here, x and y, okay, x and y are the variables here, x and y, okay, and sum and s and c out. So s and c out means it is sum and carry out. Okay, so here x, okay, x and y are input, so Cin is for this, for full adder, so we are not considering here. So now, as I told, so x instead of a and b they have taken as x and y, x is 0, y is 0. Okay, it is nothing but like 0 plus 0, so 0 plus 0, 0 only, then 0 plus 1, so 0 plus 1 sum is, means we are talking about only sum, no? 0 plus 0 sum is 0, 0 plus 1 sum is 1. Similarly 1 plus 0 sum is 1. Okay, so now here in this case this is a sum, what we are representing is a sum. So what about carry is, so none of the bits are generated here, so carry is 0. So here also carry is 0, here also carry is 0. Okay, so in all 3 combinations, 0 plus 0, 0 plus 1, and 1 plus 0, sum is 1 and carry is 0 here. Okay, similarly the last combination, 1 plus 1, so this is x and this is y, 1 plus 1, 1 plus 1 means here 1 plus 1 it will be, so 1 plus 1 it is 1 0. Okay, means the carry is 1 here, okay, 1 plus 1 sum is 0, the carry is 1. Okay, this is sum and carry is that is 1. Okay, so if 1 plus 1, sum is 0, carry is 1. So if you take in decimal also, so what is 1 plus 1? So 1 plus 1 in decimal it is 2. In decimal it is 2. 2 how we will represent in binary? That is with 1 0, means 2 raised to 0 plus 2 raised to 1. Okay, so now this is what so means 0 into is basically not 0 into 2 raised to 0 plus, okay, so 1 into 2 raised to 1, second position. Okay, so this will be 0 and this will be 2 and the overall value is 2. Means first we need to understand what is binary addition, means 1 bit binary addition. This we call as 1 bit binary addition. 0 plus 1, 1 plus 0 and 1 plus 1. Okay, this is 0, means sorry, sum is 0, this is carry is 0, sum is 1. Okay, here okay, sum is 1, carry is 0, and here also sum is 1, carry is 0, here sum is 0, carry is 1. Okay, so first we need to understand, we need to remember this one. If you remember the basic 1 bit binary addition clearly, then it is whatever may be the number of bits we can do the addition or addition. Okay, so now the same thing what we are seeing in the truth table of half adder. So as we know what is a truth table, so truth table will give the behavior of the circuit. So as we are seeing here, okay, so as we are seeing is 0 0 means sum 0, carry 0, the same thing what we have explained. So that is in the form of truth table. Okay, this is a half adder truth table. Okay, so if you see the truth table, then we know from the truth table, okay, so from the truth table we can write the boolean function. Okay, so if you see only for sum, okay, how many outputs are there? 2 outputs, 2 equations will be there. Sum equal to, so in which case it is 1, means in 2 case it is 1, sum of product. What we can tell for 0 1 combinations, means x bar y it is 1 plus then or xy bar or y bar x, anyone. Okay, so sum is this one, s is equal to x bar y plus y bar x. Okay, if you take the c out, okay, it is only one bit here. Okay, that is when x dot y. Okay, so if you see the boolean equation for sum and carry, they are matching with, so one is x bar y plus y bar x is nothing but the boolean equation for XOR gate. So we can call as x equal to, sorry, s equal to x, sorry, x XOR y. Okay, s equal to x XOR y, and this c out is nothing but x dot y. It is same, we can write x dot y, it is AND gate. Okay, so the truth table, if you see the boolean equation, okay, as I have written now, and if you write in SOP form, means the canonical form, just it is summation 1 comma 2, means sum of product. Okay, wherever in how many min terms are there, it is in terms of min terms. So wherever, means if xy value, okay, that is xy, the binary value 0 1, that is nothing but 1, for 1 0, that is nothing but 2. So 1 and 2 are the min terms for the sum. If you take the carry, the min term is 3 for carry. Okay, so we know truth table. After knowing the truth table, we can write the boolean functions or the canonical forms. So this one we need to implement the, by using these boolean equation we need to implement, realize the circuit using the logic circuits. Okay, so that is what the basic circuit for half adder. What we can do is, as I told earlier, the sum is nothing but x XOR y, that is nothing but XOR gate, and c out is nothing but x y. Okay, that is nothing but a AND gate here. Okay, so this is xy, and XOR gate is nothing but x XOR y. Okay, so this is the normal representation of the circuit for the half adder. Okay, so instead of XOR gate, if I want to realize using basic gates, so then whatever I have written earlier, that is s equal to x bar y plus y bar x. Okay, so then take xy, okay, xy, and here y bar means x, okay, this term xy bar, okay, by using AND gate it will generate. Then we need to generate one more term x bar y. So x is taking inverter here, and this is x bar y, and one more term is means for carry. So this is both are for summation, so both are given to the OR gate, then it will given to sum, that is plus is replaced with OR gate. Okay, this x bar, okay, once again if you see s equal to x bar y plus x y bar. Okay, so the first term is nothing but x bar y, so this is x bar y, okay, the first term, and x y bar, this is the second term, and whatever addition is there means that is by OR gate, so together it will form the sum circuit. So if you see the carry, it is straightforward, only xy, AND gate is enough, so that is a carry here. Okay, so now this is using basic gates, this is using XOR and AND gate. Okay, so with basic gates only, there are two other forms, so what we can implement. So here same x and y, here it will be y bar, and here it is x, and here OR gate means x plus y bar. Okay, x plus y bar, again it is given to the NAND gate. Okay, and here OR means that is again dot. Okay, NOR gate, NAND gate means x plus y bar into this term, that is x bar plus y, and NOT gate means NAND means it is whole bar. Okay, so if you take the whole bar, again we need to apply the De Morgan's laws. Okay, so after applying De Morgan's laws, then you will come to means then you will whatever x bar y plus y bar x, what we will get. Okay, after simplification of that. Okay, so here, and COT is nothing but here instead of xy we are taking as x bar y bar. Okay, so x bar, this is NOR gate, x bar plus y bar, again bar. Okay, again we need to apply the De Morgan's laws. Okay, then we will get the x comma y. Okay, sorry, x dot y. So here like this, these are the different the logic circuits. Okay, this is one type, second type, third type, and four types. So these are the different four types what we can realize using the means we can realize the half adder circuit. But in most of the cases we will use this term, means as the state we are getting XOR gate as one IC, AND gate as one IC, so we'll use two gates and realize the half adder. Okay, so this is the binary addition of the single bit, so that we call as half adder. So if you take the full adder, okay, so if you take the full adder, so here, so first what do you mean by full adder? So half adder means we have considered 0 plus 0, means like x and y of single bit. This is full adder means there are three variables x, y, for example z. Okay, three variables like this, x plus y plus z. Okay, even though means three whatever the three variables, the output will be like sum and carry only each of the single bit here. Okay, so usually this whatever three variables what we are calling, okay, in most of the cases, so it is addition between x and y, and third will be act as a the carry input. Third will be act as a carry input. So okay, so usually it is like it, and otherwise means usually we'll call like that, but as a for the adder it is a third input only. Okay, so basically it is addition of 3 bits. three individual bits means x, y and z. Okay, it is addition of three variables with a single bit, each of single bit. X is single bit, y is single bit, z is single bit. As I told, it is 0 plus 0 plus 0. So if you 0 plus 0 plus 0, sum is 0 and carry is 0. Okay, similarly if you take 0 0 1 and sum will be 1 and carry is 0. Okay, 0 0 1 combination. If you take 0 plus 1 plus 1, okay, then it will be the sum is 0 and carry is 1. Okay, as already we have seen, so addition with anything with x, anything with 0 means it is the same thing. For example, x plus 0, it is nothing but x only. Okay, so like that. So 0 plus 1 plus 1 means it is nothing but addition of 1 plus 1. Already we know what is 1 plus 1. The sum is 0, the carry is 1. Okay, so similarly here three variables means, so the three variables of single bit, so number of variables is 3, so there are 2 raised to 3 combination, so that is 8 combinations will be there. Okay, means like 0 0 0 0 0 0 0 1, so like this up to 1 1 1, so there will be 8 combinations. Okay, so now for that, so the addition how we can analyze is, it is nothing but as I told, if there are 3 bits like 0 1 1 or 1 1 1 plus 1 plus 1, if it is like this, first add these two. 0 plus 1 half adder, we know what is 0 plus 1, sum is 1 and carry is 0. So as it is sum is 1, you can take as 1, again addition of these two, 1 plus 1, sum is 0 and carry is 1. Okay, similarly here 1 plus 1, so 1 plus 1 means sum is 0, carry is 1. Again this 1 remaining we need to add to the sum, not to the carry. So here 1 plus 0, again sum is 1, carry is 0, so that carry plus this carry, that is nothing but 1 1. Okay, means the 1 plus 1 plus 1, the carry will be 1, sum will be 1. So how it will be 1 1 is, as I told, first 2 bits addition 1 0, that plus again it is 1, 0 plus 1 1, and here 1 plus 0, that is again 1. Okay, so like this the full adder means the 3 variable with each of single bit, so that addition we call as, means basically it is addition of the 3 variables with a single bit. Okay, so that we call as the full adder. Okay, so here is the truth table of the full adder. Here the 3 variables 0 0 0 and here the sum, and this is a carry. Okay, so 0 plus 0 plus 1, sum is 1, carry is 0, 0 1 0, sum 1, carry 0, and 0 1 plus 0 1 1, as I told, sum is 0, carry is 1, and 1 plus 0 plus 0, sum 1, carry 0, and similarly 1 0 1, sum 0, carry 1, and 1 1 0, sum 0, carry 1, and 1 plus 1 plus 1, as you have seen just now, sum 1 and carry 1. So this is the truth table. So if you see the truth table means, so here if you see the truth table, the sum for sum, what are the numbers are there, and for carry, so there are 2 boolean equations, so that is based on as we see by using the k map. Okay, if you put the k map as for sum, that is 1 1 1 1, so we can't group further. Okay, so each individual equation we need to write, so that is nothing but for sum what we are writing. Okay, so for sum, if you see like this, so for sum, that is x bar y bar cin, x bar y cin, x bar y cin bar, x y bar cin bar, and x y cin. There are 4 terms, that is min terms 1 2 4 7, 1 2 4 7, these 4 ones are there. Okay, similarly if you take the carry, it is similarly like whatever for addition, sorry this is addition only. So here there are 4 terms are there. If you simplify by using the De Morgan's laws and taking common variables, so it lead to S equal to, that is 3 variables, x XOR y XOR and c in. Okay, x XOR y XOR x XOR y XOR c in. So by using De Morgan's laws and uh, what is that, common, the taking the common things, then we will come to, this is a simplified format. Okay, it is basically XOR between the 3 variables. Okay, then if you come to the what is the carry, there are again there also the 4 ones, but if you see here in the K map, by grouping that, so it will simplify to, that is xy plus xc, means it is basically xy plus xc in plus yc. Okay, that is a carry. It means if you consider as a b c as variables, it's nothing but ab plus bc plus ca. Okay, so by simplifying we will get that. Okay, so now by using the K map we can get that. So after seeing the Boolean functions for sum and carry, so we need to realize those equations by using the circuits. Okay, so that it can be done in like half adder many ways. So here one of the way, so as there are 4, the terms are there for sum, 4 terms, 1 2 3 4 terms are there, then 4 AND gates, 4 AND gates for each term, that is x bar y bar c, that is x bar y bar c means 0 0 1, like this first one, and 0 1 0 and 1 0 0 and 1 1 1. Okay, so all these, the 4 expressions, and together it is added with OR gate and given. Similarly for carry, 3 terms, 3 AND gates. Okay, so whatever x bar is required initially, we have the NOT gate here. If we need x bar, use this. We need x, use this. Similarly y bar and y, z bar and c in bar and c in. Okay, so basically this connection we can, wherever it is required, we can give like that. Okay, so now this is one of the way in which we can realize the full adder circuit by using basic gates. Okay, instead of basic gates, carry we can keep it same. So here the carry we are keeping it same by using basic gates. The only thing, whatever the simplified format as x XOR y XOR c in, that we can implement using the 2 XOR gates. Means that is basically xy give to XOR gate, and whatever c in is there, that again give one more XOR gate and sum. So it is nothing but x XOR y, and this is c in, and again it is x XOR y XOR c in by using 2 XOR gates. Okay, this is one more the way what we can realize the full adder. Okay, so there is one more realization is there, that using the full adder using the 2 half adders. Okay, so means the 2 half adders. So here this is 1 half adder, already we know half adder means 1 XOR and 1 and this is one more half adder, and this is the OR gate here. Okay, so how the connection, xy sum is same like the previously, this is x XOR y and sin is given here. Okay, and this is x XOR y XOR sin. Okay, and here this is xy, okay, plus, okay, and here c in dot, so this sin is tabbed here, c in dot x XOR y. Okay, so whatever x XOR y as one of the input for AND gate, and c in is one more AND gate, so that will become c in dot x XOR y plus xy. So this term, okay, that together if we add, then we will get the CO. Okay, so this is more common used the full adder circuit. Okay, by using the two half adders. Okay, this is 1 half adder, this is 1 half adder. So this is regarding the realizing, okay, the binary adders using the basic gates and XOR or using half adder components. Okay, so now, so after seeing half adder, then it is a half subtractor. Okay, so a half subtractor. So as we know, the half adder, the two single bits. Similarly here, half subtractor is two single bits like x and y. If you take like this, okay, that is 0 minus 0, and difference is 0 and borrow is 0, and 0 minus 1, and different here 0 minus 1. So we can't subtract, means 0 minus 1. So 0, in 0 we can't subtract 1, so we need to take one extra 1. So 1 0 minus 1 means it is 1. Okay, so it is 1 0 minus 1. It is basically 1 0 is nothing but 2, and here it is 1. Okay, it is 1 0 minus 1 is 1, it is 0 here. Okay, means here, so 2 minus 1 is 1, that is sum. If you come to the borrow here, means we have taken one borrow here. Okay, 0 minus 1, we can't subtract 1 from 0, so we need to take one borrow. So that is 1 0 minus, it is nothing but 1 0 minus 1, difference is 1, and whatever borrow we have taken, that is 1. Okay, okay, that is 1. Means here we need to keep in mind, so 0 minus 1 means difference will be 1 and borrow will be 1. Similarly, if you take the third combination, that is 1 minus 0, it is straightforward. 1 minus 0 is difference is 1, borrow is 0, and 1 minus 1, it is straightforward, difference is 0 and borrow is 0. Okay, so this is how the basic binary subtraction for single bit, that we call as half subtractor. Okay, the same thing. So what we are seeing here in the truth table. Okay, so if inputs are 0 0, difference is 0, borrow is 0. If 0 1, difference is 1, borrow is 1. If this is 1 0, difference is 1, borrow is 0, and 1 1, difference is 0 and borrow is 0. Okay, so this is what is half subtraction of the single bit. The same thing, if you see here, this is matches with again like XOR only, that is x bar y plus x y bar. And if you take the borrow, okay, if you take the borrow, okay, if you take the borrow here, then it will be, it is x bar y, means for x bar y combination it is 1. Okay, so in that case what we can, means min terms for difference we can tell as 1 2 as min terms, and for borrow 1 is a min term, so that whatever x bar y is there, this is x bar y using NOT gate, and y is connected, this is AND gate, and this will be x bar y. Okay, so this circuit we call as the realization of half subtractor using the gates. Okay, so this is Boolean equation, and this is truth table, and this is the min terms with respect to half adder. So basically we need to understand here. So this is basically 0 minus 0, what will happen, 0 minus 1, 1 minus 0, and 1 minus 1. Okay, so if you remember this, then the full subtractor, it will be easy to understand. Okay, so after seeing this half subtractor, then we need to see the full subtractor here. Okay, so the full as we explained in the full adder, it is nothing but full subtractor is nothing but again, so 3 bits of subtraction here, 3 variables with single bit, that is 0. If it is like this, then it is subtract 0 minus 0, again 0 minus 0, whatever result is there, again minus 0. Okay, so as it is all are 0, difference is 0, sum is, sorry, borrow is 0. So if you take 0 0 1, so what will happen here, 0 0 1, as I said earlier also, first you take these 2 bits, 0 minus 0. What is 0 minus 0? Difference is 0, borrow is 0. So it is nothing but, if you take, it is nothing but 0 minus 1 only. What is 0 minus 1? Okay, so we can't subtract 1 from 0, so we need to take one borrow here, so difference will be 1, sum will be 1. Okay, so this is the for 0 minus 0 minus 1. Okay, in that case it is nothing but 0 minus 1, then difference will be 1, borrow will be 1 here. Okay, so if you take the next example, for example 0 1 0. Okay, 0 1 0. In that case, first you manually you can do 0 minus 1 only. What is 0 minus 1? As I said just now, borrow 1, difference 1. In that, the minus 0. So minus 0 means the difference will be 1. Okay, and the borrow will be 1. Same thing, same it will remain. Okay, so the same thing we can see here, 0 0 1, the difference and borrow are 1. At similarly at the same case again 0 1 0, difference is 1, borrow is 1. Okay, and if you take for example 1 0 1, okay, the straightforward. Okay, so 0 is nothing but, don't consider here, means don't consider in the sense, okay, we can do with 1 0. So what is 1 0 subtraction? Okay, difference is 1, borrow is 0. The same thing again minus 1, this one if you take here, and 1 minus 1 0, and this is straightforward 0 0 0. Okay, you can see here 1 not 1, outputs are 0 0. Okay, similarly the 1 1 0, and if you do these two, 1 minus 1, okay, difference is 0, sum is 0. So anything with 0 subtraction means obviously it is 0 0 only, so 0 0 here. Okay, and if you take the last combination 0 1 1 1, if you take like this, so it's most important. So here 1, first to do only this one, 1 minus 1. Okay, it is nothing but difference is 0, borrow is 0. Again it is nothing but 0 minus 1. Already we know borrow is 1, difference is 1 1 1. So what we are saying here. Okay, so this we call as the full subtractor, that is subtraction of the three variables with a single bit. Okay, so here the same the min terms what we are saying 1 2 4 7. Similarly as the min terms for difference is same as the sum in the full adder, and the min terms for the carry, that is 1 2 3 7. Okay, the same thing, the carry is after simplification we are getting, so not carry, so borrow here. So after simplification we are getting x bar y bar, x bar b, and y bar b in. Okay, so b in is nothing but as a third input. So the realizing this boolean function and the same like sum in the full subtractor, so difference is also nothing but x XOR b XOR x XOR b in XOR y. Okay, the same thing here. So what we are circuit, what we are saying. Okay, so this similarly like summer, like difference is also as I told now, x XOR y XOR b in. Okay, and if you consider the difference here, okay, so difference, so we need to realize this function, that is x bar y. Okay, so this is not x bar y bar, it is x bar y, the first term, then x bar b in, then y b in. So all are given to the OR gate, and we will get the, so whatever the borrowed boolean equation is there, that we are realized using this circuit. Okay, so this is the realization of the full subtractor and the truth table of full subtractor. Okay, and realization using basic gates, and this is half adder, and we have seen full adder and half adder, started with half adder. Okay, so now after seeing adders, the basic adder, half adder, full adder, and half subtractor, full subtractor, okay, there is one more we call as the cascading full adder. Okay, so cascading full adder is nothing but, okay, cascading in the sense the combining full adders. So as we are seeing the diagram here, this is one full adder, one full adder, one full adder, one full adder. So there are 4 full adders are there. Okay, 1 2 3 4. There are 4 full adders are there. So one full adder, we know what do you mean by one full adder. If you take one full adder, so there are 3 inputs will be there. Okay, you can take all 3 there or whatever. So 3 inputs and 2 outputs will be there, like sum and carry, and here it is x, y and z. Okay, so full adder means 3 inputs and 2 outputs. Okay, the same thing what we are seeing, the 3 inputs and 1 output. Again 3 input, 1 output. Again 3 input, 1 output. Again 3 input and 1 output. 2 outputs. 3 inputs here and 2 inputs, 2 outputs, 1 output here, 1 output here. And again here this output will act as input for this, and 3 inputs and 2 outputs. Again this output is act as input for third adder, and 3 inputs, 2 outputs, and here 3 inputs and 2 outputs. Okay, so this we call as the cascaded full adder. So one full adder is connected to the other full adder. So how it will be utilized, means where it will be used. So it will be used when there are where the number of the addition will be in more than 1 bit, the variable with the more than 1 bit. For example, if there are 2 variables like a and b with each of 4 bits, for example, each of 4 bit means 1110 and 1011. I want to add this number and this number. Okay, so in decimal this is nothing but 14, and here 1011 it's nothing but 11. Okay, 8421 code if you apply, so this will be 14 and this will be 11. So if I want to add the 14 plus 11, so in decimal it will be 25. In decimal it will be 25. Okay, so let us take carry. Okay, suppose there are 2 variables a and b with 4 bits, each of 4 bit. This is 4 bit, this is 4 bit. Okay, and c in means for the module as adder, these are 2 inputs and there is one more input as carry. So that carry I will take as 0, and there will be 2 outputs like sum and c out. And as we know, the addition of 4 bits, okay, 4 bit addition, the always the output will be, the sum will be 4 bits only, and anyway carry out will be single bit. Okay, the same thing if you see manually here 1110 and 1011, if you do the addition, okay, I will do manual addition. 0 plus 1, okay, sum is 1 and carry anyway it is 0, no need to mention. 0 plus 1, sum is 1, carry is 0. And again 1 plus 1, 1 plus 1 means the sum is 0 and carry is 1. Again 1 plus 1, okay, sum is 0, carry is 1. Again here 1 plus 1 plus 1, already we know in the full ladder 1 plus 1 plus 1, so the sum will be 1 and carry will be 1. So if you take this as whole number addition of this, that is 14 plus 11. Okay, if you put the 8421 code here, 8421, and here it will be 16. So 16 plus 8, 24. Okay, 16 plus 8, 24. 24 plus 1, 25. So as I said, the result is 25, so which is matching with the here. Okay, so this we call as the 4-bit binary addition. This is 4-bit and this is 4-bit. Obviously sum will be 4 bits and this will be the carry. This will be carry and this will be sum. Okay, so how to realize this 4-bit addition? Okay, this 4-bit addition we can realize by using 4 full adders. Okay, how it is, like as I told a and b, if you instead of a and b, so if I take x and y, so it will be as I told 4 bits. Okay, and this will be x0, x1, x2, and x3, and similarly here y0, y1, y2 and y3. Okay, so x is 4 bits, individual bit will be recognized by x0, x1, x2, x3. Similarly y0, y1, y2, y3. Okay, so now x0, x1 means if it is 1110 and 1011, as I said earlier, so the first pair 0 plus 1, the first pair x and y, so 0, okay, 0 will be here and 1 will be connected here, and C in, as I told, the scene let us consider as here it is grounded, so it is considered 0. So 0 plus 1 plus 0. So what is the sum here? Sum will be 1. 0 plus 1. Sum is 0. 0 plus 1 plus 0. Sum is 1. Carry is 0. So this output carry is connected as input for next full adder. In next full adder, what are the bits we need to consider? What are the bits we need to consider here? Okay, so that is 1 0 1 1, what I have told. The first pair is over, second pair is 1 1. So 1 1 we need to apply here, and carry input is 0, and 1 plus 1, sum is 0 and carry is 1. This carry will be connected to next full adder. What is the next combination? 1 0. So 1 0 and this carry input is 1. So 1 plus 0 plus 1, sum is 0 and again carry is 1. Again last input 1 1. So 1 1 1. Okay, sum is 0. Sum is 1 and this carry is 1. So together if you see the answer 1 1 0 0 1. Okay, so what we have seen manually previously, this will lead to 25. Okay, so this is how by cascading the full adders, okay, by cascading full adders we can add the many number of the bits, means many number of bits we can add. For example, now here we are considering 4-bit adder. 4-bit adder in the sense 2 variables each of 4 bit, like 1110 and 1011. Similarly we can have 8-bit adder, 12-bit adder, 6-bit adder, whatever it is. So how many bits adders are there? Okay, if it is 4-bit, 4 full adders. If it is 8-bit, 8 full adders. If it is 12-bit, 12 full adders. So we can use by using the full adder circuit. Okay, so this is what we call as the cascaded full adder circuit. Okay, how we can realize the 4-bit full adder using the full adders. And one more thing, only the first full adder we can replace with half adder, because usually the carry will be 0. Okay, I want to add only A and B, I don't have third input initially, so the first carry will act as 0, so we can use only half adder, because half adder has 2 inputs and 2 outputs. Okay, from the next we need to use full adder only, because if carry generates, it will act as 3 inputs. Okay, but first one we can use the half adder. Okay, so either you can use half adder or use full adder with C as 0. Okay, so now there is one more concept. Okay, means this is regarding the whatever we have seen now, this is regarding the addition of the 4-bit adder, means addition of 4 bits. So now propagation delay means, so what time it will take when we started giving the input, means when we gave the input x and y, and at what time we will get the outputs sum and carry. Okay, so if you take the full adder circuit, we have used 2 half adders, one OR gate. Okay, one OR gate. Okay, so here in the half adder we have used one XOR, one AND. Here also one XOR, one AND. Totally how many gates? 1 2 3 4 5 gates. Okay, so now suppose here XOR gate is nothing but 7486. So 7486 is the IC name for XOR gate. Similarly for AND gate 7408 is the IC name for AND gate. Okay, and one more, okay, for one more for 4 input OR gate, because for 4 input OR gate IC name is 802. IC name is 802. Okay, so here, okay, so here means the what is the propagation delay. So if it is 4-bit adder is there, at what time I have given the value of x and y, and what time I am getting sum and carry output. What is the time between, okay, from input to the output? When I gave the value, for example 14 and 11 I am giving here, at what time I am getting 25. So what is the time required from input to output? That we call as propagation delay. Okay, so why it will take delay is because each gate as 08, 802 or 86, each gate will take the time. Okay, so this is TPLH, TPHL means low to high and high to low. Okay, if any gate, if there is a transition at output, for example if you take AND gate, for example I will give 1 1 1 1 means output should come 1. Maybe initially value is 0 1, initial value is 0 1, at that time it will be 0. After some time I will give 1 1, so 1 1 means it will become 0 to 1. So how much time it will take when I give 1 1, how much time it will take from 0 to 1? Okay, so that time, okay, from when I give 1 1, at what time it will become 0 to 1, so that we call as a propagation delay. So each gate in this delay will be given in the data sheet of each IC. Okay, so each gate will take the time, okay, for transition time from input to output. So that delay they have given here 6 nanosecond for AND gate and 4 nanosecond for OR gate and 8 nanosecond for XOR gate. Okay, so like this, if you see, for if you take the sum, what is the sum? This is one XOR gate and here one more XOR gate. 2 XOR gate we are using. So one XOR gate it will take 8 nanosecond, one more XOR gate it will take 8 nanosecond. So 8 nanosecond plus 8 nanosecond together it will take, so 16 nanosecond. If I give the input now, for example XY, okay, after 16 nanosecond I will get the output at sum. Okay, this is what we call as propagation delay, 8 plus 8. What is the path? Through the path, how many gates we are using, what is the delay with respect to that gate. Okay, so similarly if you take carry, so carry, so what I am using, I am using 1 half adder, I am using 1 half adder. Okay, so after that Cin I am using, after that that one more AND gate I am using, after that this one, and Cin again I am using with a OR gate here. Okay, so in XOR gate, which is the maximum among XOR and AND gate? XOR is, if it is 8 and 6, so which is the maximum? 8. Okay, 8 I will consider. Okay, when both are in parallel, I am giving same input, when both are in parallel, so 8 will be maximum. When both are parallel, I need to consider maximum. When it is in series, I need to add, as I added previously for some, like XOR. Okay, again XOR, I added 8 plus 8 in series. If it is in parallel, whichever is maximum I need to consider, so that maximum is 8. One more, okay, so one more okay, that is maximum as 8. One more is AND gate. Okay, after that OR gate is 5. Okay, that is 5. So 8 plus 6 plus 5, so together it is 19 nanosecond for carry C out. This is for one full adder. This is for one full adder, means for one full adder sum will take 16 nanosecond and carry will take 19 nanosecond. Okay, single adder. Okay, so if you consider overall, okay, so if you consider overall, so 3 into 11, So total overall 52 nanosecond it will be considered for 4-bit full adder here. Okay, so actually at a time I am giving all the inputs. Okay, I am giving all the inputs. So at the same time the first XOR will be calculated. So after that XOR first half adder it will be calculated in all the things at the initial stage. Next whatever carry is there, so that will take the time. Okay, so together we are seeing 90 nanosecond plus 3 into, so 90 nanosecond out of 16 nanosecond and 19 nanosecond, this is for sum and this is for carry. Whichever is maximum, 19 is maximum. So I can say that one full adder it will take 19 nanosecond maximum to complete both the things, because both will happen parallelly. Okay, so individually if you take, this is 16, this is 19, but overall if you take, okay, when I give the inputs by 19 nanosecond both will be available, because by 16 sum will be available, by 19 carry will be available, together it is 19 nanosecond. Okay, so 19 nanosecond. Next 3, okay, it is 6 plus 5, that is AND or this is what is AND and OR, that is 11 nanosecond into the 3 full adders. Okay, so together it is 3 into 33 plus 19, together it is 52. Okay, so if you this will be more clear when we draw the circuit individually, and if you put these values, so it will be more clear. So at a time we are applying all the values. Okay, but it depends on the carry when it will take, when it will come. After that this will be calculated. Okay, so this is regarding what is the cascading full adders. Okay, cascading full adders and how to calculate propagation delay, and full subtractor, half subtractor, half adder, full adder, half subtractor. Okay, so all those things. Okay, so today we have seen how to do the binary addition, how to do binary subtraction with 2 single bit variables and 3 single bit variables, and cascaded addition, that is 4-bit addition.